In this lesson, we'll take a look at another objection to hypothesis testing called Lindley's paradox. And this paradox is really related to evidence from a hypothesis test rejecting a null hypothesis when intuitively it seems as though that evidence should support the null hypothesis. And often this paradox is described in terms of a series of hypothesis tests, each one having the same null and alternative hypothesis and the same population from which you're sampling, but sampling more and more units from that population. And so that's sort of what's being described in this table here. So let's first set up this hypothesis test. This is from the Hausen and Urbach book that we've read a little bit from. So their hypothesis test concerns a null hypothesis that 40% of tulips in a large and unopened delivery box are red, and therefore 60% of them are blue. So the null hypothesis that 40% of them are red, and we might seek evidence to reject that, say if we get from some sample of this box a large percentage in that sample, something large, well over 40%. So, the sort of background assumption here, which may be a little bit silly, but is for the sake of argument, is that this box is so large that we can continue to sample many, many of these tulips and still not exhaust the whole population, which is, true in lots of hypothesis tests. Seems a little bit silly for a delivery box, but we'll have to imagine that this box is huge. And so let's assume for this hypothesis test that the alpha, or the type 1 error rate, is 5%, and that we would reject the null hypothesis if we got a p-value that was less than 0.05. And that p-value would always be associated with some proportion of red tulips. And so if we imagined a sample of size 10, that's the first row here in this table. A sample of size 10, to get a p-value less than 5%, it would require a proportion of red tulips in the sample to be 70%. So that means with a small sample, you sort of need large evidence, a large deviation from 40% in order to reject the null hypothesis. And if we go to a sample of 20, the proportion of red tulips in that sample needed to reject at the 5% level drops. It drops to 60%. And so what we're seeing is as we get a larger sample, the sample proportion that would cause a rejection of the null hypothesis, well, it seems to get closer to the null hypothesis itself. And that pattern continues as you get a larger and larger sample. So, consider going to 100, a sample size of 100. The sample proportion that would cause you to reject the null hypothesis is now 48%. So seeing 48% of the tulips in a sample of size 100 would cause you to reject the null hypothesis that 40% of the tulips in the whole population, right, this whole box. So that seems counterintuitive in a way. And obviously, if you keep going, you see in this table here that as the sample size gets larger and larger, this proportion gets closer and closer to the null hypothesis. And, the intuition here, and many people defend this intuition, is that as you get a sample proportion this close to the null hypothesis, that's actually really good evidence that the null hypothesis is true. It wouldn't be a reason to reject the null hypothesis. It would be a reason to accept it or corroborate it or build up evidence for it. And that's Lindley's paradox. It's this tension between the intuition that we have that a sample proportion very close to the null hypothesis should cause us to hold on to the null hypothesis and even corroborate it or confirm it. But in fact, the hypothesis test says that we should reject the null hypothesis in favor of some alternative. That's important. What that some alternative is something we should talk about. But, a sample proportion very close to the null hypothesis population proportion is a reason for rejection according to frequentist logic. We haven't said anything about this power column yet. Remember, the power of the test is 1 minus the type 2 error, so it's the probability of rejecting the null when the null hypothesis is false. So it's not an error, it's a desired result. And you'll see that the power also increases as we get a larger and larger sample size. So we're correctly rejecting the null at a higher and higher rate as we get a larger sample size, even though the sample proportion is converging to the null hypothesis proportion. So all that seems a bit paradoxical. Now, what would the frequentists say in defense of this paradox? Well, one thing that they'll say is that a hypothesis test with a really large sample size is very sensitive to small changes from the null hypothesis. So basically, if you have a huge sample size, you will often reject the null hypothesis when your sample proportion is quite close to the value under the null. And that's just because a really large sample is a very sensitive test. It's detecting very small differences, very small deviations from the null hypothesis. So in some sense, a frequentist could say this is not really a bug, it's a feature of hypothesis testing, that the more information you have in your data from a large sample size, the better detection mechanism you have to detect really small differences. And they might say, if you want to detect large differences, you might want to use a sample size that's not quite as large, say as 100,000, that would get you a very small detection. And there are some other methods for trying to estimate the actual effect size and detecting effect sizes of at least a certain amount. And severity, this notion of severity is one possibility that can help make a little bit more sense of Lindley's paradox, and we'll talk about severity in a future lesson.